Hi folks, Mr. Long here. We're going to do a video on using derivatives to understand the shape of x-intercepts on what are called radical functions, or sometimes called composite functions. There's this little difference between radical functions and composite functions. You've studied composite functions and advanced functions. We've studied them. The square root is an example of a radical function that's not really a composite function, but we generally lump them in together, and I'll show you why just in a second here. Okay, so let's get going. Okay, so what we want to do here is understand the idea of radical and composite functions. So radical functions are any functions that have roots in them. Okay? Any functions at all that have roots in them. So for example, y equals root x. That's a radical function. Okay. So, oh, whoops. Sorry, make these radical functions here. Can you see that? Yeah, you can. So radical functions, y equals root x. Y equals the square root of x squared minus 6x. Now that's a radical function, but it's also a composite function, right? Because there's a function inside a function. And you could have another radical function might be y, whoops, probably have a pen to be better, y equals the cube root of x plus 3. That's a radical function. What are some other functions that don't necessarily look like radical functions, but they are? What if you had x plus 5 to the 6 over 7? That's definitely a composite function. Sorry, you can't really see that 6, can you? There. Now you can. X plus 5 to the 6 over 7. Now, why is that a radical function? Well, it's definitely a composite because we can see that there's a function inside a function, right? So there's a function inside that function, but why is it also a radical function? Well, again, remember our rules for exponents. So y equals x plus 5, that's the 7th root, right? The 7th root, and then I know that the x plus 5 is to the exponent of 6. So that's got a radical in it. So anytime you have a fractional exponent, there's a radical there, right? It's just represented a different way. So that is a radical function, and it is a composite function. So a composite function is any function that's embedded in another function, or sorry, a composite function is a function that has one function embedded in another function. A radical function is any function that can be represented with a square root in the numerator or denominator. Okay, those are radical functions. So you can have rational functions that are radical. In fact, the proper definition of rational functions is that they are polynomials in the top and the bottom. Okay, so anyway, so it actually, a rational function can't have a root in it, a square root of x. So hopefully that helps you understand the idea of when we say radical and composite functions, we don't really mean the exact same thing because, well, here's a composite function, y equals 2 bracket sine x plus 1 to the 7th. Okay, so it's not a very good sign. So sine x plus 1 to the 7th, that's definitely a composite function, but there is nothing to do with, and you know, why is it a composite function? Because there's that function inside the function, right? Sine x is inside that. Okay, so I think now we've got our ideas around what we mean by composite and radical functions. So let's take a look at our investigation. So the investigation that we're going to work with today is this one here. We're going to look at different radical functions. Hopefully you've printed this out, by the way, and you can fill it in as we go through. I'll be doing part of the investigation, you'll be doing the other part independently. You know what? So we're going to use derivatives, just like we used in the prior knowledge. We used the derivative of x cubed to understand its shape. So let's go through and start doing this. I'm going to do the third one with you, and then you're going to do the first two to help you understand. So hopefully you can see that okay. So the first thing we're going to do is, that's the cube root of x squared, which is x to the 2 over 3. So we're going to graph this, and we're going to find what the shape of the x-intercept is at x equals 0. Because if you look at this, right, it's pretty automatic. How would you make that y value worth 0? Well, you'd let x be 0. So we know there's an x-intercept at x equals 0. Now let's think about this for a second. What's the domain for this function? Okay, so what's the domain? So this is where you really have to start asking questions. So you look at the x. So I always look at, can I have positives, can I have negatives, can I have 0? So positives, can I have a positive, can I square a positive number? Can I have a 0 and square it? Yeah. Can I have a negative and square it? Yep. The answers of all of those are either 0 or positive. Can I take a cube root of those answers? Sure. So I'm not limited. X can be anything. I can square and then cube root any number at all. So the domain for this is just x belongs to the real numbers, okay? X is anything. Now what's the derivative of this? X to the 2/3. So we're going to use our power rule. So bring the 2 over 3 to the front of the fraction. Then I'm going to have x to the 2 over 3 minus 1. Now I'm going to represent 1 as 3 over 3 because that's a little bit easier. And then let's see here. That's going to end up being 2 over 3. X to the 2/3 minus 3/3 is negative 1/3. Okay, how do I write that? Well, negative means division, so I have to bring it in the denominator. So it's going to be 2 over 3x to the 1/3, which I can write again as 2 over 3 cube root of x. Okay, so that's our derivative. The derivatives, the two ways that are really acceptable to write that are those two. You don't want to leave it with negative exponents. So that's the derivative of x to the 2/3. Now, what's the domain for this? Well, let's think through this. So now I've got an x in the denominator. What would happen? So think positives, negatives, 0. If I put a negative number there, would I get an answer? Can I take the cube root of a negative number? Yeah, for sure I can. Yeah. So negatives are okay. What about positives? Can I take the cube root of a positive number? For sure. And then, well, then that would become the denominator. So it's 2 divided by that. What about 0 though? I have 2. Okay, this 2 divided by, if I plugged in 0 there, 0 times 3 is 0. So I have 2 divided by 0. Am I allowed to do that? No, I can't. So what's the domain of the derivative? X cannot equal 0, but x belongs to the real numbers. Okay, x can't be 0. So that means it can be anything else. Okay, anything else at all. All right, so now we know that. Let's start going through this. So we're going to use this derivative here to help us understand the shape of the graph. And all we're thinking about, like a lot about asymptotes in this section, okay? We're thinking a lot about numbers that get really big and really small. So I want to ask you, let's see here. What is a number that is really, really, really big? So what about 1 divided by 0.001? Is that a big number or a small number? Well, really what you're asking is how many times does 1/1000ths go into 1? That's 1,000. 1 divided by negative 0.004. Is that a big number or a small number? Well, it's a big number because 0.004 goes into 1 many times, and it's negative, so a big negative. That's how I'm going to write these. So a small negative I would write like this, and a big negative, again, I would write like this. Okay, so let's look at what our derivative is worth. Okay, so just on the graph, we're going to mark on 0, 0 on the negative side, 0 on the positive side. Okay, 0 on the negative side and 0 on the positive side. So think of 0 on the negative side as negative 0.00001. Think of 0 on the positive side as 0.0001, something like that. Okay, so let's make a table. And this is for x and then y prime, the derivative. So what we're going to do is we're going to check what's the value of the derivative on either side of 0. Okay, so the first one is going to be 0 on the negative side. Then I'm going to sub in 0. Then I'm going to sub in 0 on the positive side into the equation right here. Okay, so let's start with this. So I'm going to sub in 0 on the negative side. What does 0 on the negative side mean? Is it 0? No, it's very close to 0, but it's not 0. So it's a really small negative. Okay, a really small negative. So what's the cube root of a really small negative? Is it a positive or a negative? Well, it's a negative. The cube root of a negative is a negative. So that would just be another small negative. So I have 2 divided by 3 times a really small negative. So the 3 is really irrelevant. So 2 divided by a really small negative. How many times, so let's look at this. So 2 divided by a really small negative. 2 divided by a really small negative. What does that work out to? A huge negative. A great big negative, right? Okay, what about 0? What if I put a 0 here? 2 divided by 0 is infinite, does not exist. Okay, DNE. DNE. And now, what if I put 0 on the positive side? If I substituted that in for x, okay, into the derivative. So if I replace 0 on the positive side, that's 0.001, like a positive version of that. 2 divided by a really small positive is a really big positive. So this time I've got a huge positive number. Okay, what does this represent here? What does this y prime represent? Is that the value of the function or the slope of the original function? Well, that's the slope of the original function. Oh, by the way, let's make sure we plot on here. What is the value of this function when x equals 0, the original function? So if I put x into this original function, what is the value? What is 0 to the exponent 2 over 3? Or, in other words, 0 squared cube root. Still 0, I think, right? So, whoops, do that. I'm not sure. Just 1 second here, folks. I'm going to figure this out. Okay, so now let's take a look at what is the role of the slope in the shape of the graph, the shape of the x-intercept at x equals 0. So what I'm going to do here is I'm going to draw on that x-intercept, which we know is 0. Okay, this is for the original function now, the original function. So let's see here. If I'm going to go back up to this, so when x is on the left side of 0, the slope is really, really negative. Well, a really negative slope looks like that, right? And a really positive slope looks like that. And the slope there is undefined, right? I shouldn't say does not exist, I should say undefined, which means it's a vertical asymptote, right? So on the derivative, so it's super, super steep. So in fact, right for an instant, the slope here is vertical, right at 0. Okay, it's vertical. It's a very small vertical. But then look at this. To the right, it's super steep over here. To the left, it's also super steep, but it's negative. Okay, so that's what that graph looks like at the x-intercept. We call that a two-sided cusp. Okay? And we can tell from our analysis of the derivative. On the left side, it's really negative. On the right side, it's really positive. And at 0, it's DNE. So what's important here is this. At x equals 0 on the original function, the function is defined. And at x equals 0, y equals 0. But on the derivative at x equals 0, the derivative is not defined. When that happens, so if f of x defined, f prime of x is DNE, or undefined, we have a critical value that might be a vertical tangent, okay? A tangent that is, so the curve is vertical, okay? Because the slope is infinite, right? Think about this. So remember the slope is 2 over 3 cube root of x. If I put a number really close to 0 in there, this whole number is huge. So that means the slope is almost vertical. It's almost an infinite slope. On one side, the left side, it's negative. On the right side, it's positive. Okay, so the graph looks like this. it has a really weird, I call this the seagull graph, because if you complete the graph, it ends up looking like this and this. Okay, so I'm just going to finish off this table here that I probably should have looked at, or that we should probably look at. So let's go through and finish this here before I pause it and have you complete the rest of the handout. So let's look here and let's analyze this work that we've done. So it says, part A says, and again, I'm at the even odd x-intercept, and it refers to even odd because the fraction is 2 over 3. Okay, so in the exponent. So the value of f at the x-intercept of x equals 0 is defined or not defined. Well, we know that the value of f, it is defined. Does f prime have a vertical asymptote? Well, we know that f prime, or y prime in this case, was 2 over 3 cube root of x. Well, definitely there's a vertical asymptote. X can't be 0, right? And on either side, it's approaching positive, or one side negative infinity, the other side positive infinity for the slope. Okay, the value of f prime at the x-intercept is not defined, right? Because x can't be 0 on the derivative. Okay, here's this important piece here that we did with our table. The values of f prime near the x-intercept, so near the x-intercept. Our choices can be positive, negative, that's like negative, like just regular positive, negative numbers like -5, +7. 0 on the negative side, 0 on the positive side, so in other words, the curve is very flat, like x cubed or x to the 4th. But the slope can also be negative infinity, positive infinity. Well, that's our scenario, right? Because we know that it looks like this, so it's almost a vertical line. So as x approaches 0 on the negative side, that's the left side, we knew the slope was negative, and it's approaching negative infinity, right? Because when I substitute a small negative into here, that becomes, the whole bottom becomes negative, and then it's 2 divided by a super small negative, which is negative infinity. So the slope is negative infinity approaching from the left, which makes perfect sense given our graph. As x approaches 0 on the positive side, it's going to be positive infinity because that's a very small positive number. 2 divided by a very small positive number is a huge positive number. Positive infinity, in fact. Okay, then let's look at this. There is a change in sign across the x-intercept for f. So did f change going across the x-intercept in sign? Did it go positive to negative? No, it didn't, right? It didn't change sign. It was just like this. Right, there's your x-intercept right there. There was no change in sign. It didn't go positive to negative. So what all of this information, this part E, or I should say F, this summarizes everything that you've done above. It tells me that at the x-intercept, the function is vertical, right? Because there's infinite slope there. Is the tangent one-sided, or sorry, is the function one-sided or two-sided there? In other words, does the function exist on both sides of the x-intercept? And the answer is yes, it does. Okay, it's two-sided. Remember, square root of x is like the square root of x will be one-sided. Does it have a local max or min there? Or neither? Well, look at that. That's a local min. And it's not really a local min officially is a nice smooth curve like that. It is a minimum, right? It is a minimum, and it's local too. So I do believe that we should consider that a local minimum. It's not in the traditional sense, right? But it is a local minimum. So conclusion: the x-intercept is a one-sided cusp, a two-sided cusp. It's a two-sided cusp, and it has a minimum. Okay. And remember, a stationary point can be a min, a max, or a saddle. So we're just adding to the variety of points that you can make. Okay, so now what you're going to do, folks, is go back through, and you're going to do the even root and the odd root, and you're going to do your little table of 0 on the negative side, 0 and 0 on the positive side, and work through those. Okay, and then we'll take that up in a few minutes. All right, so let's pause there, and you can work through those. Okay, folks, let's take this up quickly. And this really is it's critical to understanding. A lot of times this kind of stuff just gets presented as factual, but that is a very limited, well, you don't have any understanding at all, right? So I know it's painful to go through this, but it will really help you understand the nature of why curves are shaped the way they are. Okay, so let's look at the odd root then, the one in the middle. So this is x to the 1/3. What kind of numbers? Can I cube root a negative? Yes. Can I cube root 0? Yes. Can I cube root a positive? Yes. Do the derivative. When you simplify it, you'll end up with something like this. That's your f prime of x. Okay, 1/3 x squared cube root. Okay, think of BEDMAS. You square first, then you cube root. So now x belongs to the real numbers, but what can't x equal? 0, right? You can't, x can't be 0 because you can't divide by 0. Now, can you have a negative in there? Can you have a negative right there? What do you think? Can we have a negative here? If I square a negative, I get a positive, then I take the cube root. Yeah, that's fine. That's fine. Okay, checking left and right. 0 on the negative side means I take that, make it really small, square it. I get a positive, but it's still really small. 1 divided by a really small number is a huge positive. Okay, something subtle here that I was making a mistake with earlier. Sometimes I refer to does not exist and undefined as the same. Does not exist is something like a limit does not exist. What we say when we're dividing by 0, we say that the result is undefined. It's not does not exist, right? It's because there's a calculation that you make there. You divide by 0. It's just really undefined. So does not exist means you can't even enter into a calculation, whereas undefined means you can enter into a calculation, but the answer just doesn't make a lot of sense. So I should have subtly mentioned that. So at x equals 0, the slope is undefined. It's not that it doesn't exist, it's just undefined. There is slope, it's vertical. Okay, so something that does exist, but you can't quantify would be undefined. All right, so we know that that's the shape of the graph then, right? So as we get our shape of our graph, we know that the slope is undefined in the middle, right? Because we're dividing by 0. Okay, we're dividing by 0 here. So I know what I showed here is that there is a vertical slope there. Okay, so there's a vertical slope. And whoops, let's move that up. And there's a vertical slope, and then to the left, whoops, to the left the slope is quite positive. Okay, so down here the slope is very, very positive. And then the slope to the right on the 0 side is also very, very positive. Okay, so that's what the shape of a cube root graph looks like. Okay, with calculus reasons. Okay, that's what it looks like. That's the slope of a what's the shape of a cube root function. Okay, let's look below at our answers really quickly. I'll let you look at those, folks. I'm not going to bother going through them. The one thing I do want to note with you is for the last part, which should be G, I forgot one shape, and it's the odd root shape. That's what this is. It's an odd root, x to the 1/3 or cube root of x. It has a very characteristic shape, an odd root. So an odd root, it does this. It's vertical slope, but then it gets less and less on one side, less and less on the other. But it does, there is a change of sign across, so we do have an x-intercept that crosses. We just don't have a max or min. Okay, let's look at square root. And I know this is a pretty long screencast, by the way, but hopefully you paused and did some work in between it. So square root 1, you know what, you can't get the square root of a negative. You cannot get the, you can't take the square root of, this is for the derivative, right? Because the derivative, if you look, it's 1/2 root x. And so we cannot have 0. We also can't have a negative. So here we can't even enter into that calculation because negatives can't go under a root sign. Here we can make that attempt to divide by 0, and it's a vertical slope, so it does look like this, right, at the origin. And then what happens after that? Well, there's nothing to the left, so none of this over here exists, but going to the right, it's a huge positive. So what's that? Okay, so there's your classic square root graph. Okay, x to the 1/2 or the square root of x, and that's why at this location it has a vertical slope at the origin at 0, 0, and then it gradually gets less and less steep as it moves to the right. Okay, and again, as you fill in the information, I'll leave that there. What I'm going to do is come down to the bottom. That should have been f and g. So this information tells me that f at x at the x-intercept is vertical. Okay, we can see that because we're dividing by 0 in the derivative. It's one-sided. We can see that very clearly because the derivative is not defined for negatives. And a lot of people would think, because it looks like this, that you would call this a local minimum. To be defined as a local minimum or maximum, you have to be able to enter that point from both sides. And since you can't enter this point here from both sides, it's neither a local maximum nor a local minimum. So really, it has neither. It would be an endpoint probably on an interval because you can't go any further to the left. So it's neither. And then we call this a one-sided cusp. Okay, a one-sided cusp. So now we understand that cusps, there's a two-sided cusp and there's a one-sided cusp right there. Cusps have a vertical slope. Okay, they have a, whoops, should have gone up here. Cusps have a vertical slope there and there. All right, folks, so now hopefully you've got a good set of notes there. You know the general shapes for those three curves. Let's, you know what, let's just quickly summarize them. So for y equals x to the 1/2 root of x, our graph looks a certain way. Y equals x to the 1/3, it looks a certain way. And then y equals x to the 2/3, it looks a certain way. And there's your square root graph. There is your cube root graph. And then there's x to the 2/3, the seagull graph. What is common with all of those? Vertical tangent, vertical tangent, vertical tangent. Okay, the slope is undefined at x equals 0, and it's vertical. All right, otherwise they are different, and you can do that just by checking the derivative on either side of the x-intercept. Okay. Now, what I would suggest you do right now is again more practice. And the practice I'd like you to do is, boy, that's hard to see, isn't it? That's x to the 1/4, x to the 1/5, and x to the 4/5. And try to graph each of those. Okay, use your calculus to get the shape on either side. Okay, so go ahead and try that, and you can use Desmos to see if you're right or wrong. Okay, so again, take the derivative, do that table, and then see what the shape of the curve is on either side of the x-intercept of x equals 0. Okay, hopefully this helps, and you've got a nice set of notes there to work on, and you understand why radical functions have the shapes that they do at their x-intercepts.